Hello dear learners, I welcome you all to the third module, that is Introduction to Magnetism of the SWAYAM MOOC on Electricity and Electrical Wiring. I am Dr. Smritimala Sharma, Assistant Professor in Physics, B. Borwa College. Module 3 has been divided into 3 units. In Unit 1, you have learned about magnetic properties of materials. Here, we have covered the basic magnetic parameters and different types of magnetic materials like paramagnetism, dimagnetism, and ferromagnetism. In the second unit of this module, we will focus on magnetic hysteresis, hysteresis loop, retentivity, coercivity, importance of hysteresis in electrical wiring, soft and hard magnetic materials. Now, what is magnetic hysteresis? Magnetic hysteresis refers to the phenomenon where the magnetization of a material depends not only on the current magnetic field applied to it, but also on the material's previous magnetic history. The term hysteresis means lagging. Hysteresis is characterized as a lag of magnetization or magnetic flux density behind the applied magnetic field or intensity of magnetic field. All the ferromagnetic materials exhibit hysteresis phenomena. When a ferromagnetic material is magnetized in one direction, it will not relax back to zero magnetization when the imposed magnetizing field is removed. Magnetization must be driven back to zero by a field in the opposite direction. If an alternating magnetic field is applied to the material, its magnetization will trace out a loop called a hysteresis loop. The lack of retraceability of the magnetization curve is the property called hysteresis, and it is related to the existence of magnetic domains in the materials. Once the magnetic domains are reoriented, it takes some energy to turn them back again. This property of ferromagnetic materials is useful as a magnetic memory. Some compositions of ferromagnetic materials will retain an imposed magnetization indefinitely and are useful as permanent magnets. The magnetic memory aspects of iron and chromium oxides make them useful in audio tape recording and for the magnetic storage of data on computer disk. Let us now move to hysteresis loop. The magnetic hysteresis effect is often visualized in a graph known as hysteresis loop, which plots the material's magnetization or magnetic flux density versus the applied magnetic field or intensity of magnetic field. This loop illustrates how the magnetization changes as the external field is increased, decreased, and then increased again. The hysteresis loop is typically plotted with the x-axis representing the applied magnetic field or intensity of magnetic field, while the y-axis representing the magnetization or magnetic flux density of the material. The loop is formed as the magnetic field is gradually increased, decreased, and then increased again. Thus, it illustrates how the material responds at different stages of the applied field. Let us understand the different stages in a typical hysteresis loop. When you apply a magnetic field to an initially unmagnetized material, the material begins to magnetize as the magnetic domains within it align with the field. The magnetization increases gradually with the increase in the applied field. At first, this increase is linear or nearly linear as the magnetic domains are oriented with the field. As the field strength increases further, the magnetization continues to rise until the material reaches saturation magnetization, where most of the material's magnetic domains are aligned in the direction of the applied field. After this point, increasing the external magnetic field further does not significantly increase the magnetization, since almost all the domains are aligned. The curve flattens at this stage, representing magnetic saturation. Once the external magnetic field is reduced to zero and then reversed, the magnetization doesn't follow the same path it took during the initial magnetization. The material remembers its previous magnetization, and this leads to hysteresis. The magnetization begins to decrease but at a different rate due to the material's reluctance to change its magnetization immediately. As the reverse magnetic field increases, the magnetization decreases and the material reaches a point where the magnetization becomes zero. This occurs when the field strength reaches the coercivity or coercive field, which is the field required to demagnetize the material. The coercive force is the magnitude of the reverse field needed to cancel the magnetization. At this point, the material has no net magnetization. When the external magnetic field is removed completely, the material retains some magnetization. This is known as remanent magnetization, and it reflects how much of the material's magnetic domains remain aligned after the field is zeroed out. Remanence is a key property for permanent magnets, which retain their magnetization even without an external field. When the magnetic field is reversed again, the magnetization follows a different path, reaching negative saturation in the opposite direction. Eventually, as the magnetic field returns to its original direction, the magnetization returns to its original state, completing the loop. So this is how actually a hysteresis loop forms.
In this video, we're going to be going over how the hysteresis loop is formed. And what we mean by this hysteresis loop, it's a characteristic of, say, some sort of metal as to its retention of magnetism. So whether it retains magnetism or not. And so we're going to walk through this and hopefully you'll get a better understanding of exactly how this all kind of plays together. So what we have here is we have an x-axis and a y-axis. Our x-axis is labeled H. And what that means is magnetizing force. What magnetizing force is the force needed to create flux lines. Our y-axis here, you notice, has the B, which is our flux lines. It's Tesla, so how many flux lines are being created. This little line here is our magnetizing curve. So what's happened here is, if you can see, as we increase our magnetizing force in, say, some sort of iron core or steel core, it could be any kind of metal, then you're going to see that the flux lines increase. So again, we're talking about a wire wrapped around a core. So we're basically creating an electromagnet. So this, as we increase our magnetizing force, then our flux lines increase until they get to a certain point. And that point is called our point of saturation, which means that no matter how much magnetizing force you can put on this, if we keep increasing it, you can't put any more flux lines into that piece of metal. Because it gets to a point where it's like the toothpicks, when you're putting toothpicks into the little toothpick bottle, it gets to a point where it's all full. And so we hit saturation. So we're going to see what happens when we do that. We magnetize it. And then if we get rid of our magnetizing force, let's see what happens to this. As we get rid of our magnetizing force, so our magnetizing force goes back to zero, you'll notice that it retains some flux lines. This doesn't just drop out like that. What happens is the flux lines, there are some that retain or stay. So that might not be a good thing. You might want to get rid of those flux lines. So what we call this, though, is our point of retentivity or retention, which we're going to denote with that R. Now, if we want to get rid of this, what we have to do is put a magnetizing intensity on it in the opposite direction. So we gave it a positive magnetizing force, which created this magnetic line here, and then hit saturation. We turned it off and went back here. We still have some retaining of magnetism here. So in order to get rid of it, we push it the other way, which could drop our our flux lines down to zero. Now we call that coercive force, which we're going to denote with the C here. Now if we somehow just kind of kept this magnetizing force going, it ends up creating another line like this, but an inverse line in this direction. So you see that it keeps going until it hits that saturation point again, but in the opposite direction. And then the same thing follows true. So it's going in the opposite direction. Then we realize that we've left the magnetizing force on in the opposite direction. If we turn that off, what should happen, it should be the inverse of what happened up here. So we should see it drop back and retain some magnetism, but in the opposite direction, which is exactly what has happened here. So we've retained some magnetic lines of force in the structure itself, but in the opposite of direction of what they were there. So again, in order to get rid of this, we're going to have to coerce it into the other direction. Now, before we do that, we have to note that it is retained here as well. So we had retention up on the positive side, and we have retention on the bottom as well. Then we are going to coerce it back. So we put some more magnetic intensity on it in the opposite direction, and we can get rid of all those flux lines. We end up with a flux of 0 at this point too. And again, if we left the magnetizing force on in that direction, it would continue to go. So again, we had to coerce it. So this is our coercive force at this point here, which we can see with the big C. So again, if we were not paying attention and we left our magnetizing force on, what's going to happen is it's going to go in this direction again and still hit saturation and see what happens here. And we can see that it goes back and hits that point again of saturation, and the whole thing continues again. So what we end up with is what's called the hysteresis loop. Now, when we have cores that have a skinny hysteresis loop, meaning that when we let go of this and it goes back down close to 0, that is something that does not retain a lot of electromagnetism, which is something that would be good for, say, like a transformer or a coil, because you don't want it to retain that magnetism. Whereas if you're trying to create a big, huge electromagnet, you want to have it kind of come up top here. So what we talk about is how a hysteresis loop for an electromagnet, something that you want to have retain its magnetism, is going to be relatively large or fat compared to if you have an iron core or something for a transformer or a relay or a coil. You want that to be skinny. So it's going to kind of, as soon as you get rid of the magnetic intensity, that's going to drop down closer.
Let us discuss retentivity now in details. The retentivity or remanence of a material is defined as the amount of magnetization that remains after the external magnetic field has been removed. This remanent magnetization is a direct measure of the material's ability to remember its past magnetic state. Materials with high retentivity are capable of maintaining a significant portion of their magnetization even when the external field is absent, which is desirable for applications such as permanent magnets. Retentivity is primarily determined by the alignment and movement of magnetic domains within a material. Magnetic domains are regions within the material where the magnetic moments of the atoms are aligned in the same direction. When a magnetic field is applied, the domains tend to grow in size as they align with the field. Upon removal of the external field, some domains may remain aligned, causing a permanent magnetization in the material. However, not all domains stay aligned when the external field is removed. The extent of alignment and therefore the retentivity depends on several factors. For example, the domain structure. A material's ability to retain magnetization depends on the ease with which the domains can return to their original positions after the field is removed. Retentivity also depends upon anisotropy of the material. Materials with high magnetic anisotropy, which means that the material has preferred directions for magnetization, typically show higher retentivity. Retentivity also depends upon temperature. The retentivity of a material decreases with the increasing temperature. Let us now discuss the importance of retentivity in various applications. One of the most common uses of materials with high retentivity is in the manufacture of permanent magnets. These magnets are used in electric motors, generators, hard drives, magnetic resonance imaging, and various other devices where a stable magnetic field is required over time. Materials with lower retentivity are often preferred in transformers and inductors because they minimize energy losses due to retentivity, which can lead to unwanted heat generation. Let us now discuss coercivity in details. Coercivity refers to a material's ability to resist changes in its magnetic state when exposed to an external magnetic field. It is defined as the intensity of the external magnetic field required to reduce the magnetization of a material to 0 after it has been magnetized to saturation. It plays a critical role in determining the performance of a magnetic material in a variety of applications, from data storage devices to electric motors and magnetic sensors. There are two types of coercivity in materials: high coercivity and low coercivity. Materials with high coercivity require a significant external magnetic field to alter their magnetization. These materials are typically used in applications where stability and resistance to external magnetic field are essential. Examples of high coercivity materials include permanent magnets like those made from rare earth metals. The materials with low coercivity are easily demagnetized or magnetized and are typically used in applications where frequent changes in the magnetic field are required. These materials are often used in transformer cores, electromagnets, and magnetic recording medium. Soft magnetic materials such as iron, silicon, steel exhibit low coercivity. Coercivity is a crucial property for understanding and optimizing magnetic materials for a range of practical applications. High coercivity is essential for materials used in permanent magnets. Permanent magnets such as those used in motors, loudspeakers, and data storage devices need to maintain their magnetization over time without easily being demagnetized by external influences. High coercivity materials like neodymium iron boron magnets exhibit excellent stability and strength, making them ideal for these applications. In magnetic data storage devices such as hard drives and magnetic tapes, coercivity is crucial for information retention. The ability to write and erase data relies on the material's response to external magnetic fields. Materials with the right coercivity allow for reliable data writing and prevent unintended data loss due to external magnetic interference. Materials with low coercivity such as soft iron are used in transformers, electric motors, and inductors. In these applications, the material's magnetization needs to change quickly in response to alternating magnetic fields. Low coercivity allows the material to respond swiftly to changes in the applied field, making it ideal for these dynamic applications. Several factors influence the coercivity of a material, including the crystalline structure of the material, its grain size, temperature, and composition. Materials with a more ordered or regular crystalline structure tend to have higher coercivity because the magnetic moments align more easily and resist changes in magnetization. Smaller grains tend to reduce the material's coercivity as they allow for easier realignment of magnetic domains. Larger grains, on the other hand, increases coercivity as it becomes harder for the domains to reorient. Coercivity generally decreases with the increasing temperature. As temperature rises, the thermal energy of the system increases, causing greater movement of magnetic domains and making it easier for the material to become demagnetized. Coercivity depends upon composition of the materials. Adding certain elements to a ferromagnetic material such as cobalt in iron can increase coercivity by altering the material's magnetic properties and structure. Dear learners, let us now go through a small quiz to test your understanding. Hope you have enjoyed the quiz. Let us now move to the next topic of our lecture. In this topic, we are going to learn how hysteresis affects the electrical wiring. Hysteresis plays an important role in the behavior of materials used in electrical wiring and electrical components. although it is more commonly associated with magnetic materials than with the wiring itself. However, the principles of hysteresis have implications for the efficiency, performance, and energy losses of various electrical devices that rely on magnetic fields such as transformers, electric motors, and inductors. Hysteresis loss is a form of energy loss due to the lag between the applied magnetic field and the magnetization of the material. When the field changes, the magnetic domains within the core material resist realignment, causing energy to be dissipated as heat. The area enclosed by the hysteresis loop represents the energy loss or the hysteresis loss. Hysteresis in magnetic materials leads to energy losses in the form of heat, which impacts the efficiency of electrical systems. The energy dissipated as heat can increase the thermal load on electrical components, potentially damaging insulation of the materials or other components connected to electrical wiring. Minimizing hysteresis loss is essential for improving the overall efficiency and reliability of the electrical system that use magnetic components. Electrical components, wirings, and insulation systems need to be designed to cope with hysteresis losses by using materials with low hysteresis and ensuring that adequate cooling and thermal management are in the place. The next topic of our discussion is the types of magnetic materials depending upon hysteresis loop. Depending upon the hysteresis loop, the materials can be divided into two types: soft and hard magnetic materials. Soft magnetic materials are materials that are easily magnetized and demagnetized. These materials have low coercivity and low remanent magnetization, meaning they require only a small magnetic field to become magnetized, and they lose their magnetization easily once the external magnetic field is removed. We are moving to the characteristic of soft magnetic materials. As we have already discussed, the soft magnetic materials have low coercivity. These materials require only a small external magnetic field to reverse their magnetization. They retain very little magnetization after the external magnetic field is removed. They have high magnetic permeability. These materials are very easy to magnetize and demagnetize. Examples of soft magnetic materials are iron, silicon steel, ferrites, nickel cobalt alloys. Soft magnetic materials are used in transformers, electric motors, magnetic shieldings, MRI, etc. Hard magnetic materials, in contrast, are materials that are difficult to magnetize and difficult to demagnetize. These materials have high coercivity and high remanent magnetization or retentivity, meaning that they retain their magnetization even after the external magnetic field is removed. They are often used in applications where permanent magnetism is required. If we move to the characteristic of hard magnetic materials, they have high coercivity, they have high remanence, they have low magnetic permeability, and they are difficult to magnetize and demagnetize. Examples of hard magnetic materials are alnico, which is a combination of aluminum, nickel, and cobalt. These alloys are used in permanent magnets, especially in loudspeakers and electric motors. Samarium cobalt alloy, niobium iron boron alloy, ceramic ferrites. These are the examples of hard magnetic materials. These hard magnetic materials find application in permanent magnets, electric motors, data storage, magnetic coupling, etc. Dear learners, let us quickly go for the differences between soft and hard magnetic materials. The main distinction between soft and hard magnetic materials can be summarized as: in case of hard magnetic materials, they are difficult to magnetize, they have high coercivity, they have high retentivity, while in case of soft magnetic materials, they can be easily magnetized and demagnetized. Their coercivity and retentivity are less. Dear learners, we have come to the end of this session. Let us go through a quiz. Hope you have enjoyed this session. Let us quickly summarize the topics discussed. We have learned about magnetic hysteresis, how to draw a hysteresis loop, how coercivity and retentivity affect the performances of various magnetic devices, the importance of hysteresis in electrical wiring, and classification of materials depending on hysteresis loop, that is soft and hard magnetic materials. Thank you for joining this lecture, and I hope it has provided valuable insights into the world of magnetic hysteresis and its importance in electrical systems. Thank you very much.